Is it visible?
Yes, sir.
Yes, sir.
Okay. So welcome all of you. Now, today I would like to discuss about some electronic properties of materials. Last 2 weeks, I think, we have discussed about the mechanical. Or last week I have discussed about the mechanical properties of materials. So this is the electronic. Now we come to electronic properties of materials. So electronic properties. Now materials of many of these properties you know already, so I quickly just review those properties so that you will refresh yourself the relevant properties which is necessary for making or for modeling or for consuming purpose some of the new devices, MEMS based devices using semiconductor material. Okay, so one important property is energy band gap, and energy band gap is known to you, all of you know about that. Okay, uh, so there are four electrons that take part on bonding to adjacent atoms because of this 3s2 3p2. So here there should be 6 capability but 4 less that is why these are the 4 valence electron which are taking part in current conduction mechanism. So those 4 electrons are can easily detached from the silicon because these are not closely bound to the nucleus. So electrons can have discrete quantum states, because energy band is coming from the concept of discrete energy quantum states. Okay, so band gap, which is also known as forbidden gap, that is a result when a crystal is formed and the energy states overlap. Okay, so here is the conduction band. This is the valence band. So this is the forbidden gap. Okay, so the gap between the conduction band and the valence band, which is known as band gap, and it is defined by Eg. Okay, so potentials of some atoms overlap and results in a certain of energy bands, and this energy band gap is created, and these are all known to you. So now free carriers are those that can cross the band gap using thermal energy and take part on conduction mechanism. So that so that means for conduction you need some electrons which are free, and that is all possible if you from valence band some electrons are transported into the conduction band. Okay, by applying energy. So there are three kinds of materials: insulator, semiconductor, and metal. So in case of insulator, we know the band gap is extremely large, and it's for silicon dioxide is also insulator. It has a band gap. It has got the band gap of 8 electron volt. Okay, on the other hand, like for example diamond, okay, it has 5 electron volt band gap. So these are the band gap of insulator materials, and it will be very difficult for transporting electrons from valence to conduction band in case of silicon dioxide or in diamond, because it needs enormous amount of energy. If you want to transfer electron from valence to conduction band, you need very high energy. Okay, so on the other hand, another extreme case is a metal. and metals have no gaps, or it may be having very small gap, because the conduction band to valence band, here see it is overlapped, and in this case is extremely narrow band gap in some of the materials available. So there even a small amount of energy, enormous amount of electrons will be transported or transformed from valence band to conduction band, and as a result um, electron density is extremely high, and it will have very high large conductivity. Okay. Here semiconductor is another the last one, third category of the material. Here the band gap in case of silicon is approx 1.12. Okay, or in case of germanium it is more likely to have 0.67 electron volt at room temperature. Okay, and on thermal energy, the electrons are excited from valence band to conduction band, and those electrons will take part in current conduction mechanism. So as a result, what happened? The transfer of electrons from valence to conduction band, some vacancies will be created which are known as holes, all of you know. And so in semiconductor, in intrinsic semiconductor, basically both electrons and hole take part in current conduction mechanism. And in band gap, energy levels are quantum levels are mechanically disallowed. Okay. Valence band is the actually highest energy band completely filled with electrons at 0 Kelvin. On the other end, and electrons can be excited in next empty band, which is known as a conduction band. So these are the definitions. So now for intrinsic semiconductor, it does not have any impurity and conductivity, which is provided by thermal excited electrons, because there is no impurities doped in intrinsic semiconductor. So impurity atoms will not, okay, impurity electrons will not take part in a current conduction. Only intrinsic electrons which are available, they will take part in current conduction. So obviously its conductivity will not be very high, and the distribution of electrons over the bands is given by the Fermi function. Okay, and which is basically equal to, say, Fe equal to 1 by 1 plus e to the power of e minus ef by kt, where ef, that is the Fermi level energy, and k is the Boltzmann constant, and t is the absolute temperature in Kelvin. Okay, so all these things have already been read in, I think, first year. All of you have read it. So Fermi function gives you the probability that an electron state at a particular energy level that will be occupied, and it explains the behavior of an intrinsic semiconductor. Okay, so Fermi level lies within the valence band in a metal. So now these are the picture of probability of electron in the conduction band, and the probability of jump from valence band to conduction band shows in these three diagrams. One is at 0 Kelvin. Here is the temperature is a little bit more than 0 in this. This is in 0, this is more than 0, and this is it's large compared to 0 Kelvin, high temperature. Okay, so you see at 0 Kelvin in conduction, when there is no electron, but if you increase the temperature from 0 Kelvin to a certain extent, so small amount of electron um, uh, will be jumping to the conduction band. Okay, so valence band to conduction band. And so as a result, if the probability with a Fermi function, because of the Fermi functions, you will have the probability of very small probability of electron in the conduction band. But at the same time, we increase the temperature from medium to high, so a lot of electrons will jump, and you have seen here in this case, um, the probability of occupying states in the conduction band will be larger, as a result of which the conductivity will be higher. Okay, this position. So now I will discuss on the extrinsic semiconductor. So extrinsic semiconductor, here you have to dope some extrinsic impurity materials, and because of doping of the material, if you dope impurity atoms which have to go higher level of the silicon, that means for example, higher group, if you dope with a phosphorus atoms or arsenic atoms, which is having 5 electrons in the outmost orbit. So here if it replaces a silicon there, so then extra one silicon uh, one silicon there, so extra electron is available for conduction. So here you see, in addition to the thermally generated electron, you are having much more carrier, and these are free carriers from the impurity atoms. Now impurity atom, if you dope to a larger extent, so there are two kinds of carriers. So one's the thermally generated carriers, in addition to the extra carriers available from the impurity atom. So both the carriers will take part in current conduction mechanism. So as a result, to be conductivity will be higher in case of extensive semiconductor in time. And on the other hand, if you look into the p-type semiconductor, then the dopant atoms are obviously the valence electrons will be less than the silicon. Either group of 3 elements will be doped here, like boron or aluminum or indium may be doped there. So here indium uh, is dopant, uses dopant. So there are the valence electrons is all less. So obviously one vacancy is created if a silicon is replaced by an impurity atom. So now that vacancy will be filled by some extra electron which is available because of thermal generation energy. So as a consequence of that, the electron which is coming from other place to fill the vacancy there, so as a result, to be there is a movement of the so movement of the vacancy, and you will have some current in the semiconductor material. So those are the basic mechanism of n-type and p-type semiconductor conductivity and current conduction mechanism in case of extrinsic semiconductor. Okay, now the another property which is very important property of the semiconductor is the mobility. So mobility is defined as the drift velocity of the carriers per unit potential gradient. So it is generated by the term mu equal and its unit is centimeter square per volt second. So now there is a lot of phenomena which changes the mobility property. One is the doping concentration. If the doping concentrations are more in a crystal, so then the mobility may degrade, because it doping are more, so lot of carriers will be there, and there will be chances of high collisions, and because of the enhanced collision probability, so mobility may reduce. So high concentration in extrinsic semiconductor, in some cases mobility degrades, okay, reduces, and basically in that case it is a measure of ease of movement through the lattice. Okay. If the collisions are less, so mobility will be higher. Electrons actually will have a higher mobility than holes, owing to the lower mass of electrons. That is why, you know, in case of n-type semiconductor, the mobility is very high compared to the p-type semiconductor. Electron mobility is higher than hole mobility. We know it because electron will have a lower mass. Mobility is a function actually of crystal quality, material defects, interface quantity, doping density, stress, and temperature. These are various parameters which change the value of the mobility. Okay, so you can change the value of the mobility this according to these parameters. Now, resistivity, that is another important property, and that is also known to you. Resistivity is in a semiconductor bar is given by rho into L by A, where L is the length of the semiconductor material and A is the cross-sectional area. So okay, rho is the resistivity. Okay, now on the other hand, R is given by rho into L by A, which is given by W into T. A equals to W into T, which is basically the conductivity. Okay, is given by it's given by here 1 by rho, which is this is the conductivity, and it is given by Q into uh, mu n plus mu p p, where mu n, which is called the electron mobility, and mu p, that is called the hole mobility. Okay, and n and p are electron and hole concentration. Q is the electronic charge. So mu decreases with increasing scattering events. If scatterings are more, mu value it decreased. So if their impurity atoms are more, so where the scattering probability will be more. In that case, mu also decreases. So these are known as impurity scattering. There another scattering which is known as a lattice scattering. Because of that, also mobility can uh, decrease. Okay, it is degrade. Next property is the piezo resistivity. Uh, that is another electronic property of the semiconductor material, which is very important and which is used for making microsensors. Either it is many kinds of microsensor, MEMS based microsensors like the pressure sensors, gyro sensors, accelerometers, the gyroscope. There are based on the piezoresistive property of silicon materials. Uh, you can use this property into various MEMS based devices. Okay, now what is piezoresistivity? It is a property where the bulk resistivity is changed by mechanical stresses applied to the material. If you apply mechanical stresses force on a bulk material, then its property, particularly resistivity, will change. That is piezoresistivity. Now why it is changing? It is because of different reasons. Okay, number one, uh, it's a change of carrier. Mobility will take place if you apply pressure on a particular semiconductor body. There is a possibility of change of carrier mobility. Okay, second is the change of number of uh, charge carriers as a function of volume of material. So if we apply stress on a body, its volume may change, and because of change of volume, the number of the charge carriers may change, and because of that, also resistivity may change. Because resistivity it is added to mobility, resistivity related to the charge carrier with doping concentration. Okay, is not it? So because of these two changes, the resistivity may also change. Okay, the third parameter is the volume volume change, which affects the energy gap between valence band and the conduction band. Okay, that is another property, important electronic property. If you apply pressure or stress on a particular semiconductor material, its band gap, that means energy gap between the conduction and valence band, may change. And because of the change of the band gap, there is a change. You will be change in carrier density. Okay, because if band gap reduces, so more and more there is a possibility more electrons from valence band cross the band gap and it will reach the conduction band. So as a result of which resistivity will change. Okay, so those three things, one is mobility change, another is number carrier density change, and the band gap, third is the band gap change. So because of these three changes, the resistivity will change as a result of applied pressure or stress on semiconductor material. Okay, so now let us discuss a little bit details on the piezo resistivity effect. Although all materials have piezo resistance effect to some extent, single crystal silicon has a high piezo resistivity along with excellent mechanical property. A piezo resistance property that is available uh, in most of the materials, but in some cases it is very small, in some cases very large. Okay, so fortunately silicon material will have very large piezo resistance effect and along with the good mechanical property. We have already seen some of the mechanical properties in last lectures. So it is a good conduct for micro sensors. So fractional change in resistance due to applied mechanical stresses to the material is given by the relation delta R by R, which is a change is a change of resistance is given by 1 plus 2 nu delta L by L plus delta rho by rho. So here nu, that is the Poisson's ratio. So this is coming from the mechanical properties, and that is basically delta L by L, that is deformation length changes of the particular the semiconductor material with a cylindrical rectangular delta that will change, as a result of which there is a change in the Poisson's ratio value, and that is effect in the first term. Okay, second term, delta rho by rho means resistivity change, and that is because of this mobility change, number density change, and all of these things which I have discussed in last slide. So there are two things that are reflected in two terms for a cylindrical register. This expression is valid, the first term, which is usually very small, and the second term is the dominant term in case of piezo resistance property. And the second term is basically coming for two reasons. One is the mobility change, another is the band gap change. Okay, this rho by rho. Clear? So that will see how this effect is coming and what are the reasons. So delta rho by rho, the second term is of that expression is given by pi into sigma. Okay, what is the pi? What is pi? Pi is a piezo-resistive coefficient. Piezo-resistive coefficient. Okay, in general, what happened? Del rho by rho equals to mu 1, sorry, pi 1 sigma pi L sigma L plus pi T sigma T, where pi L and pi T are longitudinal and transversal resistive coefficients, and sigma L is the longitudinal stress parallel to the direction of current flow, and sigma T, that is the transversal stress perpendicular to the direction of the current flow. So these are the general equation of change of the resistivity. Now there is another term, another parameter which is known as the gauge factor, which also defined in last week. That is delta R by R divided by the epsilon, which is expressed in percent resistive changes per applied strain. That is the gauge factor. Okay, now change of the strain by application of strain, the change of resistance is basically the gauge factor. Okay, so this is the piezo. So this is the relation of electric field and the current with the resistivity tensor. So for a 3D crystal, the electric field vector is related to the current vector by 3 into 3 cos 3 resistivity tensor. So here is E1, E2, and E3. These are electric field vectors, and whereas I1, I2, I3, these are current vectors, and is related by this resistivity tensor. And if you see this particular, this row 1, row 2, row 3, basically these are resistivity tensor, and this resistivity tensor is given by this expression, and that resistivity tensor is a delta rho, delta rho 1, delta rho 2, row 3, delta row 4, 5, 6 in this way. And this in terms of pi and sigma. Okay, so for isotropic conductor, for example, in case of unstretched silicon, this is row 1, row 2, and row 3, which is equal to row, and row 4, 5, 6, these are 0. So here row 1, row 2, and row 3, these are treated as row, and row 4, row 5, row 6, these are treated as 0 for unstressed silicon. Okay, so automatically the whole thing in case of isotropic conductor, when there is no stress, then complete the E is equal to the uh, uh, sigma into I. That is the conventional relation. But for non-isotropic case, means when we apply stress, so in that condition E equal to rho into I. Okay, that is the simple relation that will not hold, because in case of different crystallographic direction, the stress component will be different, and in that case there are piezoresistivity coefficients will involve, and those piezoresistivity coefficients in different crystallographic directions are different. Okay, so these are the certain properties which I have discussed today, and I think that's all for today. If you have any queries, any doubts, you can ask me. So unmute yourself and ask me any doubt, any queries. Do you have any queries, any doubt?
No, sir.
No, not now, sir.
Okay. Devanjana, Devaraya, do you have any
No,
queries?
sir.
No, sir.
No, sir.
Okay.
Holidays